Hello everyone. I would like to discuss the design details of two line-stage amplifiers. Both amplifiers have similar structure. The first line-stage amplifier uses all bipolar transistors. The second one is similar, except that JFET transistors are used for the input stage. Both amplifiers produce low noise, low distortion, and remarkable sound. Okay, now let us dive into the design. This is the first line-stage amplifier that contains all bipolar transistors. We will walk through the design details of this amplifier in this video. Due to the length of the video, the second line-stage amplifier using JFET input stage will be shown in a separate video. This is a simple line-stage amplifier that contains 8 bipolar transistors. However, here is an even simpler line-stage amplifier that contains only 6 bipolar transistors. Let us see how it works. It contains a differential amplifier input stage using 2 NPN transistors. The second stage, which is also called voltage amplifying stage, contains a common emitter amplifier using a PNP transistor for Q3. Transistor Q4 and diodes D1, D2 works as current source for transistor Q3. The output stage is a simple emitter-follower pair. It works as a voltage buffer before the signal passing to a power amplifier. A feedback network is connected between the input stage and the output of the amplifier. Then a very simple amplifier is formed. As a matter of fact, this is one of the simplest line-stage amplifier designs that contain 3 stages. Another simple line-stage amplifier design is to use complementary transistors for the input stage and second stage. In this design, the differential amplifier input stage employs PNP transistors, which are complementary to the NPN transistors in the previous design. The second stage is also a common emitter amplifier. However, NPN transistor is now used instead of the PNP transistor. The output stage is again an emitter-follower pair, which is identical to the previous design. Obviously, they have the same output stage. What about the input stage and the second stage? From the small signal point of view, they are identical. Here is the question: can we combine the input stage and the second stage from these two designs? The answer is yes. This is how the input stage and second stage are combined together. As a matter of fact, it saves a few diodes and resistors. Here let us examine how the phase changing along each amplifying stages. For illustration purpose, let us feed a signal with positive phase into the input stage. Since transistors Q1 and Q3 work in common emitter configuration, the signal at the collector is phase inverted. When the signal's passing to the second stage, transistors Q5 and Q6 also work in common emitter configuration. The signal is inverted one more time. Negative times negative becomes positive. Therefore, the output signals from the second stage now become non-inverted, which is in phase to the original signal of the input stage. If we can think one more step ahead, since the output stage is a pair of emitter followers, which is a non-inverted amplifier with a gain of unity, the final signal appearing at the output of the line-stage amplifier is also non-inverted, which is in phase with the input signal. Here we have the combined input stage and second stage. Can we simplify this circuit a little more? Can we merge the resistor R8 to R3 and R10 to R7? Yes, indeed we can. Here's how it looks like. Eventually, after the output stage is added, the line-stage amplifier becomes this. Let us now break down the entire amplifier into several sections and discuss one by one. This is the input stage that combines 2 differential amplifiers. This is the voltage amplifying stage, or just called second stage. This is output stage that contains a pair of emitter follower. This is the output network. Finally, this is the feedback network. If you have not subscribed to the channel yet and are enjoying these kinds of videos, then hit the bell button and the subscriber button so that you will be notified immediately when a new video comes up next time. The line-stage amplifier is simplified in this diagram. A1, A2 and A3 are the voltage gain of the input stage, voltage amplifying stage, and output stage, respectively. Output network and feedback network are highlighted in blue rectangular box. They are now numbered from 1 to 5. Then we are going to discuss these sections one by one. Let us first take a look to the input stage. This is the circuit of the input stage. It contains two independent differential amplifiers. The first differential amplifier is on the top, which contains NPN transistors Q1 and Q2. The second differential amplifier is on the bottom, which contains transistors Q3 and Q4. The input stage takes the signal from the input and feedback from the output. It compares the input signal to the feedback signal and amplifies the difference of the two, then passing to the next stage, which is the voltage amplifying stage. Since the two differential amplifiers are independent, we can look at them one by one. Here we look at the differential amplifier on the top, which contains two NPN transistors. To simplify the analysis, we assume the base current is small so that the DC potential at the base is 0. Assume the base to emitter voltage required to switch on this NPN transistor is 0.65 volts. Therefore, the DC potential at point A is minus 0.65 volts. In reality, there is some base current, and the base DC potential becomes slightly below 0. Therefore, the DC potential at point A will be slightly less than minus 0.65 volts. However, this does not affect the calculation of the collector current too much. Nevertheless, we assume the DC potential at point A is minus 0.65 volts. The tail current is found to be 3.6 milliamps. The collector currents for Q1 and Q2 become 1.8 milliamps. Therefore, this is the picture of the DC bias condition of the differential amplifier on the top. Now we turn to the differential amplifier on the bottom, which contains a pair of PNP transistors, Q3 and Q4. Please note that resistor R6 has a slightly higher value than R5 in the previous case. The tail current is now 3.3 milliamps, and collector currents are 1.65 milliamps. It should be noted that because the tail resistors R5 and R6 are different, the collector currents for the top and bottom differential amplifiers are also different. 1.8 milliamps in the previous case and 1.65 milliamps in here. We will explain shortly why different collector currents are used. When combined together, they form a complementary differential amplifier pair. It has two inputs and produces two outputs feeding to the voltage amplifying stage. Let us move to the voltage amplifying stage. What the voltage amplifying stage does is to amplify the signal from the input stage, and it produces a high voltage gain so that it helps building a very high open loop gain to the entire amplifier. It also creates a DC voltage spread to bias the transistors in the output stage. When the feedback is applied, the high open loop gain will bring down the distortion and broaden the bandwidth. Here is the actual arrangement of voltage amplifying stage used in the line stage amplifier. In order to turn on a bipolar transistor, the base to emitter DC potential must be greater than the VBE of the transistor. Additionally, we also need to take into account the polarity of NPN and PNP transistors. For an NPN transistor, the base DC potential is higher than the emitter. However, for a PNP transistor, the base DC potential is lower than the emitter. Suppose the tail current for the top differential amplifier is I0. Then I0 is the sum of the collector current I1 and I2. I4 is the collector DC bias current flowing in transistors Q5 and Q6. I3 is the current flowing through resistor R3. It is clear that I3 is equal to the sum of I2 and I4. According to what desired voltage gain we want to have, choose a resistor value for R2 and R6. It is often a resistor between 1 kilo ohms to a few kilo ohms. Here we take R2 and R6 equal to 1.5 kilo ohms. In determining the resistor values for R3, R7, and R8, we juggle these resistors in such a way that transistors Q5 and Q6 are turned on, and their DC bias current, I4, is a few milliamps. It is also noted that since I3 is greater than I1, we must have R3 smaller than R2. When meeting these conditions, we finally get R3 and R7 equal to 270 ohms. Here is the schematic of the all-bipolar transistors line stage amplifier. We need to address resistors R5 and R6. You will see in a moment that the final resistor value for R5 and R6 are different. There is a reason why they are not the same. Since the input stage and the voltage amplifying stage are directly coupled, the DC bias of the voltage amplifying stage is dependent on the input stage. Since the top and bottom differential amplifiers are two independent amplifiers, they tend to fight for dominant in setting the DC bias current for the voltage amplifying stage, and also the output stage DC bias current. If we choose equal value for R5 and R6, say 3.9 kilo ohms, the output transistor Q7 has 19 milliamps DC bias current, while Q8 has 10 milliamps. This is not desirable. To solve the problem of unequal DC bias current, we have to use different resistor value for R5 and R6 so that the top and bottom differential amplifiers have slightly different DC bias current. As shown in the schematic, R5 is 3.9 kilo ohms and R6 is 4.3 kilo ohms. Then Q7 and Q8 have the same collector currents, 15 milliamps. Now we move to the output stage. The output stage is an emitter-follower pair so that it produces low output impedance, improves output current drive capability, and broad bandwidth. Here is the emitter-follower pair output stage. After transistors Q5 and Q6 are switched on, the collector current IC creates a DC voltage spread across points A and B, which is used to bias the emitter-follower pair. For this line stage amplifier, current IC is 4.7 milliamps. Therefore, the DC voltage spread is between 2.2 volts to 3.1 volts. The DC bias current for output transistor Q7 and Q8 is set to 15 milliamps. As seen earlier, here is the phase relations between the input stage and the voltage amplifying stage. For this complete amplifier with all three stages, what are phase relations among them? Since transistors Q1 and Q3 operates like a common emitter amplifier to the input signal, the signal at the collector is phase inverted. What about the phase of the signal at the collector of Q2 and Q4? Do you think it is inverted or non-inverted? Write down in the comment section in this video below. The output from the voltage amplifying stage is non-inverted. Since emitter-follower is a non-inverted amplifier, the output from this line stage amplifier is also non-inverted. Now we move to the output network. Resistor R15 and capacitor C5 forms a low-pass filter. This helps stabilize the amplifier at high frequency. Resistor R16 improves the ability to drive capacitive loads. For example, a long cable with high internal capacitance connected between this line stage amplifier and a power amplifier. Now we move to the feedback network. Resistors R9 and R10 determine the voltage gain of the entire line stage amplifier. In this amplifier, the voltage gain is 7.7 or 17.7 dB. On the other hand, global feedback also helps reduce distortion, output impedance of the amplifier, and broaden the bandwidth. Capacitor C1 stabilizes the amplifier at high frequency. There is one thing has been missing from the previous schematics so far. It is the DC servo, which is now put in this final schematic to complete the all-bipolar transistors line stage amplifier. The blue color rectangular box is the DC servo. Since the line stage amplifier's output will be further amplified by an audio power amplifier, we need to keep the output DC offset from the line stage amplifier as low as possible. Therefore, we employ a DC servo here. Here is a simplified diagram. The line stage amplifier is shown on the top, while the DC servo is shown in the blue rectangular box below. The purpose of using a DC servo is to take down the output DC offset. In this line stage amplifier, the The final output DC offset is just 2 to 3 millivolts. First of all, the DC servo samples the output from the line stage amplifier. Then it filters out all AC signal components but keeps the DC offset voltage. It is fed to the inverted input of the line stage amplifier. Since it is through the inverted input of the line stage amplifier, the filtered DC offset voltage is inverted and passed to the output. The inverted DC offset voltage appears in the output so that the net output DC offset voltage is reduced. Since the DC servo is always connected to the line stage amplifier, the amplifier's output DC offset is eventually reduced to nearly ground level. This is a short discussion how a DC servo works. If you want to know a full discussion of DC servo with various audio applications, write down in the comment section below. If there are enough people interested in it, I will make a separate video of DC servo. If you are interested in knowing more analog audio amplifier design technique, you may find this reference book useful for you. This book covers both semiconductor devices and vacuum tubes that are commonly used in audio applications. Audio amplifiers such as phonostage, line stage, power amplifier, and low noise regulated power supplies are extensively discussed, and design examples are given. This is the table of contents. It gives a quick overview what topics are covered. Chapter 2 covers the DC analysis for amplifying devices. We will expand the contents of Chapter 2 in a moment. Chapter 3 covers the AC analysis for amplifying devices. Therefore, Chapters 2 and 3 give all the necessary information for setting the DC bias, as well as determining the AC properties of various amplifier configurations in terms of voltage gain, input and output impedances. Here are the topics covered in Chapter 2. All commonly used amplifying devices such as bipolar transistors, enhancement and depletion type MOSFET, JFET and triodes are discussed. These are the topics covered in Chapter 3. All commonly used amplifying configurations such as common emitter, common collector, and common base for bipolar transistors, and similar configurations for field effect transistors and triodes, are discussed in this chapter. Compound amplifying configurations such as differential amplifier, cascode amplifier, SRPP amplifier, and white cathode follower are also covered. 4 line stage amplifiers. One chapter is dedicated to solid-state semiconductor devices and another chapter for vacuum tube devices. 4 power amplifiers. 3 chapters are dedicated to vacuum tubes, solid-state semiconductor devices, and hybrid devices separately. Expanded tables of contents for all chapters are given in the following website. The link to the website is also written in the description of this video below. Now let us take a look at the measured performances of this line stage amplifier using all bipolar transistors. In the audio band from DC to 20 kHz, the distortion plus noise is less than 0.002%. Signal-to-noise ratio is greater than 90 dB. At 1 kHz, the distortion plus noise is as low as 0.0016%. A simple design can achieve such a low level of distortion is quite remarkable. This is the second version of line stage amplifier that uses JFET transistors for the input stage. The measured performances are similar to the previous version using all bipolar transistors. However, the input stage in this version is very different. It is one just single differential amplifier rather than 2 independent differential amplifiers of the bipolar transistors version. The JFET has the self-bias feature that makes the design much easier and different from the design using bipolar transistors. The discussion of this line stage amplifier with JFET input stage will be shown in the next video. For the second version of line stage amplifier that uses JFET transistors input stage, the distortion at 1 kHz is 0.0011%, slightly lower than the bipolar version. Free PCB Gerber files are available in the following website. The link to the website is given in the description of this video below. Go to the download section and look for the PCB name LS-S1. Both versions are available. If you have not subscribed to the channel yet, and are enjoying these kinds of videos, then please think about clicking the subscriber button below so I can continue to make these videos for you. I will see you in the next one.